Good morning, good afternoon, and also good evening to everyone. Thank you very much for joining us in this, the 41st Combustion webinar. So my name is Dong Yang, and I am currently an assistant professor in the Southern University of Science and Technology in Shenzhen, China. So we started this webinar series since the 2nd of May in the last year. So that was just after about a couple of months of the quarantine at home due to the COVID pandemic. So it's very hard to believe that after going through so far to the 41st webinar, most of the world is still under lockdown. So I hope everyone and your families are healthy and safe. And I also hope that at least at the moment, you could relax a bit and enjoy the talk today from Professor Raman Sujith. So I will start with a brief introduction about Professor Raman Sujith. So he graduated with his bachelor's degree of technology in aerospace engineering from the Indian Institute of Technology in Madras in 1988 with a first rank. He then obtained his master's and a PhD's degree in the 1990s and 1994, respectively, both from the Georgia Institute of Technology. He received the award for top graduate students in the College of Engineering during that period. And after that, he then went back to join IIT Madras in 1995. And he is currently the Srivasan Chair Professor. He is a recipient of many fellowships and awards, including the Alexander von Humboldt Fellowship, the Hans Fischer Senior Fellowship, the Young Engineer Award of the Indian National Academy of Engineering, and the Swana Jayanti Fellowship, and the J.C. Bosch Fellowship. He was the founding editor-in-chief of the International Journal of Spray and Combustion Dynamics, and he is also currently a member of the editorial advisory board of CHAOS. So he's a member of the Indian National Academy of Engineering and the Indian Academy of Sciences. He currently works on the application of dynamical systems and the complicated systems theory to study and mitigate thermoacoustic instability. And this is also what he's going to talk about today. So before I give the floor to Professor Sujith, I would like to remind the audience that you are very welcome to raise questions during the talk. Please use the chat function near the bottom of the screen. Type in your questions there, and I will ask on behalf of you after the talk. So now, Professor Sujith, the floor is yours.
Thank you very much. A very good day to all of you. I think some people have night, some people have day, some people have afternoon, some people have early morning. So good day to all of you in these chaotic times. And I will speak a bit about chaos today. So I wish to thank the organizers, in particular, Dr. Isaac Box and Wenting Sun for getting me signed up for this seminar series. I really thank them for this opportunity. I also want to thank Dong Yang for this very nice introduction. I want to talk about complex system approach to investigate and mitigate thermoacoustic instability in turbulent combustors. I did a lot of the work together with Vishnu, so I just want to acknowledge him also. And I want to acknowledge the Department of Science and Technology, Office of Naval Research, Global ONRG, AFOSR, Siemens, General Electric, ISRO, GTRE, DRDO, RIC. In particular, I want to thank Dr. Ramesh Kolar and Dr. Venki Shankaran, who were really a long-time supporters and really were inspiring to get me to do this research. And I want to thank our collaborators. Without their help, none of this would have been possible. And the brilliant students, postdoc, and staff with whom I worked over the years. And so let's get straight to business. So Let's go back half a century to the past and look at the Apollo program. And I just want to play a movie. Everybody may not be familiar with combustion instability.
Try to fire it for the first time. Go apart.
So these movies are the best introduction to combustion instability. So feedback between the acoustic field and the combustion oscillations lead to very large amplitude oscillations that are catastrophic when there's a positive feedback, and you reach ruinously high amplitudes. And we have many instances where the amplitudes were well in excess of 100% of the mean chamber pressure. And thermoacoustic instability often leads to catastrophic problems, catastrophic failure in various situations. And of course, they are very dramatic in aero engines and rockets. And always it's very impressive to see these pictures of destruction. And thermoacoustic instability can introduce severe thrust oscillations, and that can cause structural failure, loss of controllability, endangering payloads and sensors, and guidance and navigation systems, and lead to partial and total mission failure. And always, like I said, the best stories told by these destruction pictures, and often the failure is catastrophic. And they are not, this instability has not spared power plants either. These are pictures from destruction of land-based gas turbine engines when people try to go to lean premix pre-vaporized systems. We had instability. This is a article from the Wall Street Journal, which talks about turbine makers are caught in an innovation trap, where they talked about the combustion instability and causing a lot of problems and shutdowns and so on and so forth. And the direct losses due to thermoacoustic instability exceeds 1 billion annually in industrial gas turbine engines. So this is quite a big loss. And so thermoacoustic instability is an acoustic phenomena. So I think we have to listen to it. So I'll play a sound of thermoacoustic instability. And this is a very simple laminar burner in a pipe. Okay, so there's nothing fancy, no turbulence, nothing. There's a simple flame. It's just a cap with 7 holes, and the laminar flames, you can see them. And I'm going to play this sound. Hope you can hear it. So these are periodic oscillations. And now I would play another case. You see, these are not periodic oscillations. They're actually, if you pay attention, they're not periodic. They're actually chaotic oscillations. So, and we use dynamical system theory to study such things. So what is a dynamical system? A dynamical system is a system that evolves in time. So if you generally describe it as dx by dt equal to f of x, where x is a list of state variables. It can be pressure, velocity, concentration, all the variables that you have. Okay, and dynamic systems can undergo bifurcation. And what's a bifurcation? It's nothing fancy. It's a small, smooth change in parameter values causes a sudden qualitative change in behavior. So this is called bifurcation. So maybe in the popular language, it's called tipping. So traditionally, thermoacoustic instability is considered a half bifurcation, and this is indeed a good way to describe thermoacoustic instability. And it's very good to describe a laminar combustor in thermoacoustic instability in laminar combustor this way. You probably know that when you talk about half bifurcation is something where a system that is having a decay changes to a system that's having growth. So below some critical parameter, the system is decaying down, whereas above some critical parameter, the system is actually, the oscillations are growing, and this changeover is called half bifurcation. So this is in very simple terms. So you can have either supercritical bifurcation or subcritical bifurcation. Again, these are simple terminologies, just the name sounds fancy, but supercritical bifurcation means If you increase the parameter, at some value, the amplitude of oscillations start growing, but they grow slowly. They don't abruptly jump. And if you reverse the direction of the parameter, the oscillations will continue in the same way, and it'll reverse the path, retrace the path, and then go back to zero. Whereas in the case of subcritical bifurcation, you have, as you increase the parameter forward, and suddenly you get a jump in the amplitude. And then if you retrace the value of the parameter, it's not going to go back, retrace the original value. You have to go back further, and then you have to reach beyond some level, and only then you get to stable point. So this is supercritical bifurcation. So there is some level of a region of hysteresis, and in this region, and also there is a basin of stability, and there is a stability boundary here. Below this hollow red circles, the system is stable. Above that, if you perturb it by an initial condition which is above that, it will go to this large amplitude limit cycle oscillations. Okay, so so bistable system shows hysteresis, and you can see it all over the place. This is a picture of a turbulent diffusion. There's laminar diffusion burner in a duct, and you see here the flame location is a parameter, and you can see this hysteresis region. You can see this is the hysteresis region, and below this point, if I keep exciting till this point, and below this red cross, you get decay, but above that, it'll grow to this limit cycle oscillation. So that's the stability boundary. Another location, yeah, till this red cross, you will get stability, but above that, you go to unstable situation. And so the nonlinear dynamics as a subject started in 1960s. I think you all know in 1963, Lawrence had this famous paper on sensitivity of the initial sensitive solution to initial conditions, and as you change initial condition a little bit, maybe in the 6th decimal or something, the trajectory takes a completely different path. So the subject was born in the 60s, and likewise this bistability, etc., were discovered at the time. And it's very interesting that at that time at Princeton, we had Professor Kroko and his students. This is a young version of Sirignano and Professor Zen. Professor Sirignano, when they were students, and they were actually, if you read those 1960s papers, they're very impressive. They were able to calculate the bistable region hysteresis, etc. in 1960s. Imagine, they didn't have this kind of computers and so on, and it's very impressive. But then from then on, somehow, although nonlinear thermoacoustics had a very good start, the focus in the 70s was on solving the whole problem with linear theory comprehensively, and it stayed that way for 40 years or 50 years till this decade, when nonlinear dynamics came back strongly. So in a dynamical system, there are a lot of variables, and and this list of variables is called state vector. And you can, if you have in the modern CFD simulation, you have very large number of variables. There are people running simulation with billion grid points, and each grid point will have several properties. So maybe you're talking about several billion, or if you are a graduate student with not so heavy computing, you're talking about millions of state variables. But and you can plot them against each other in a phase space. And of course, we can only see 3 dimensions because we are 3-dimensional beings as human beings. But we can plot one against the other, and this is called phase space, and we can visualize how the trajectory moves in the space. But if you're an experimentalist, all you have is one microphone, and maybe 2 or 3 if you are somewhat rich. But if you're in the gas turbine business or rocket business, they wouldn't let you put a lot of transducers in. So you have very limited number of transducers. And can you then study the dynamical system with things from one transducer? It turns out that it's indeed possible. It's called phase space reconstruction. And what we do is to reconstruct the phase space using something called Takin's embedding theorem. So we have a time series T, and we actually take the time series and delay it to get delayed time series. And you plot one against the other. And how do you delay? The delay is such that we calculate this quantity called average mutual information. That's the amount of information which is common between the 2 time series. And at the time delay at which this goes to minimum, that is the time delay you choose. So take P of t, P of t plus tau, P of t plus 2 tau, and then you can plot the trajectory. And how many dimensions should you do to obtain this embedding dimension, the number of dimensions in which we should embed? We determine the false crossings of the trajectory by keep on increasing the dimension system. At some point, we see the number of false neighbors will come down because there will be no more false crossing because you have enough number of dimensions, and that would be the appropriate embedding dimension. So we will try to this Abarbanel and Kantz and Schreiber, they're very nice books. I would suggest that you can read that. And so we'll look at a very simple experiment. This experiment is done by Libiga Kabiraj when she was a graduate student. Now she's a professor. So this is there's a tube which is very small, 16 mm diameter tube, and then it's bound with a cap with 7 holes. So it's the simplest possible burner, and each of the holes is 2 mm diameter, and this outer tube is 57 mm glass duct. So this is probably the simplest experiment that one can come up with. Lipiga did this brilliant experiments, and a very simple experiment, but found brilliant things with this. So this is the let's look at the experiment and under some conditions. Not able to. Yeah. Okay. So these are periodic waves. I hope you could hear it. And this is what I played at the beginning. And if you look at the pressure and heat release rate signal, the nice periodic things, I mean, it will be something like as if I drew a sine omega t here in the pressure. And if you look at the power spectral density, there's a very sharp FFTs. And if you plot the phase portrait, you will see a very nice and clean closed orbit showing a limit cycle. There's a pressure, there's a heat release rate. And then if you slice this, you'll get this Poincare section, which has discrete points. Okay. And these are limit cycle oscillations. So now I will play what is called quasi-periodic oscillations. And all I'm doing is the bifurcation parameter here is the position of the flame in the duct. So if you paid attention, you can see that there is a modulation of the acoustic field. And you can see the multiple frequencies, and you see there is many frequencies. And if you look at the phase portrait, there's actually a torus, like a donut shape, and if you slice it, you'll get these 2 closed orbits, and these are quasi-periodic oscillations. So next, we look at something more interesting. So these are chaotic oscillations, actually. The FFT looks broadband, and you would see the phase portrait. The phase portrait is very thick, and it's filled. And you see in the Poincare section, which I get by slicing the phase portrait, I see a cloud of points, and these are actually chaotic oscillations. There are a lot of systematic ways in which you can we can quantify chaos, but I will not go into that. Rather, I'll try to give you an introduction into the subject. So now, so this is the next state where you see a lot of frequencies. And if you look at the phase portrait, the trajectory it looped around, and eventually, after many loops, it came back to the original place. So that's why we don't get a donut shaped thing, but we have like some strings wrapped around, and then it came back. And the Poincare section also shows this finite number of points around the ring, and these are called frequency locked oscillations. And okay, so so these are period 2 oscillations. We can see classical period 2, the loops twice, and you can also see 2 points on each side. And these are very nice period 2 oscillations. So if you look at that, you get different type of signal as you change the flame position in the duct, and you see limit cycle oscillations, quasi-periodic oscillations, chaotic oscillations, and period 2 oscillations. So a different type of oscillations. When I was a student, I thought that either we had fixed point or quietness, or we had limit cycle. But I found that there are many more things than these things. And so you have a fixed point that the system is stable, and then we get a limit cycle oscillation. And then we have another bifurcation called Niemann-Zucker bifurcation, or secondary Hopf bifurcation. And after that, so the 2 is periodic or limit cycle oscillations, 3 is quasi-periodic oscillations. And then we have another bifurcation where the torus breaks and you get chaos. So this is called the Royal-Takens route to chaos. This is a famous route. There are only a few different routes to chaos, and this is one of them. So it's very interesting that we found this Royal-Takens route to chaos. And I wouldn't go through it in detail, but the flame dynamics is different for these different states. For limit cycle, you'll have fairly repetitive flame dynamics. Quasi-periodic, it'll be sort of like that, but it won't be exactly repetitive. And chaos is, you will see things like roll up and elongation and stretching and lift off and so on. So the flame dynamics is different. It'll take some time to describe this, so I'll just briefly say this here and go. Now, another important state is intermittency. So this is a simple Bunsen burner in a pipe, and here you can see periodic oscillations, and the flame is staying stable. In contrast, here you see that the flame is trying to intermittently lift off and fall back. And you can see the pressure time series below. So it is really intermittent sound, as in the English word intermittent, but intermittency is a proper state in dynamical system theory with a lot of with statistics that converge in the long time duration and so on. And we found the intermittency route to blowout, and Guan and Larry Lee recently have found the intermittency route to chaos in laminar thermoacoustic system, and they're a very nice piece of work. So we talked about nonlinear dynamic system, but my talk title talk about complexity. So now this is a picture which I have borrowed from the famous book of Strogatz on nonlinear dynamics and chaos. So on the horizontal axis is the number of degrees of freedom. On the vertical axis is the linearity or non-linearity. So here is, get this slide up. So here is linear, and as you go down, it's increasing non-linearity. As you move to right, it's increasing degrees of freedom. So at n equal to 1, we get things like dx by dt equal to kx, exponential growth, and things like that. N equal to 2, you get linear oscillations, and there's things like mass spring system, RLC circuit. And if you go to n very large, you get things like, you come to Avogadro number of variables, and you get equilibrium statistical mechanics, and you take n tend to infinity, and you get partial differential equation. You can write equation for elasticity, wave equation, electromagnetism, acoustics, and so on. Now at n equal to 1, you increase nonlinearity, you get things like fixed point and bifurcations and so on. N equal to 2, you start getting limit cycles. And n equal to 3 or higher, you get chaos. And as n is large, then Strogatz has marked this as a dotted line, calling it the frontier, because this is the spatiotemporal complexity. So things like cardiac arrhythmias and stuff like that, lasers, nonlinear optics come here. Our turbulent reacting flows also belong to that category. So now let's talk about complex systems. So this is an academic translator I got from my wife, where she explains how the different phrases academicians use it can be interpreted. So a complex phenomenon stands for I don't understand. So I think this is a very accurate description. I got this from my wife. But a complex system has a very specific meaning, and a system with multiple interacting components whose behavior cannot be simply inferred from the behavior of its components. So that is a complex system. And this a very good example to illustrate is this flock of birds flying and
dark clouds. The phenomena was spotted in the skies of southern Israel on Saturday. Israeli ornithologists and amateur bird watchers flocked to an open field near the southern city of.
So there are like lots of birds, I don't know, thousands of birds, and they're flying in a pattern which looks like a bird. It's amazing. And you see, this flying in a self-organized pattern, and complex systems can self-organize. Okay. So now why am I showing picture of birds and so on? So let's get to thermoacoustics. So the instantaneous phase between pressure and heat release oscillation is what decides whether you're driving your damping. And if you look at that during a stable operation, you will see that the instantaneous phase between pressure and heat release oscillations is very incoherent during stable oscillations, as you can see. It's a very nice picture taken by Vishnu. And if you look at thermoacoustic instability, you actually see very coherent structure. This is like the bird flock thing. So a high level of coherence is observed during thermoacoustic instability. This is the phase data extracted from chemiluminescence images and so on. But we see a high level of coherence in different forms during thermoacoustic instability. And often engineers or technicians refer to such coherent thermoacoustic system as something that is alive, even using terminology like the combustor is breathing. So large coherent structures emerge in turbulent flow during the occurrence of thermoacoustic instability. And such emergent behavior is a telltale sign of complex system. And the self-organization of the turbulent flow and the emergence of an ordered coherent acoustic field and these large structures, they happen by itself. And I will also show another picture during intermittency state where you can see a mix. You see incoherent coherence for some time, and then you see coherence. And this is a characteristic of complex systems. They show this mix. So we can think of a turbulent reacting flow as a complex system. Turbulence itself brings large number of interacting scales and degrees of freedom. And then there is this molecular mixing, chemical reactions, acoustic waves. And so we can view thermoacoustic instability in turbulent combustors as order emerging from chaos in a complex system. So in a reductionist approach, we would zoom in on the constituent elements of the system and analyze them in detail. We take it apart, and that is the traditional way with which we do. But in complex system approach, we do not zoom and split things apart and zoom in on the component behavior. Rather, we focus on the phenomena that can emerge from a simple set of components interacting through a simple set of variables. So what are the key ingredients of a complex system? The key ingredients of a complex system are interacting elements, the nonlinear feedback that affects the behavior of the systems, and they are open system, exchange of energy and mass with surroundings. So complex systems show emergent properties. What is emergence? So a simplest way to illustrate it is by looking at water. So there are water molecules, and there is oxygen and hydrogen in these molecules. And you can zoom in on this oxygen and hydrogen and what happens between them. But there's no way to express what is called wetness at the molecular level. Wetness is an emergent property. It originates from the interaction of the oxygen molecules, but it occurs at a large scale, the macro scale. So this is a classic example that people give for emergence. So let's look at thermoacoustic transition in a turbulent combustor. So we will first look at the time series data. And this is a time series from stable operation, which we would call combustion noise. I hope the audio is playing. You can sense it is not a tone, it's a broadband sound. I hope you are hearing it. This is the maximum volume. And now we'll look at thermoacoustic instability. This will be annoying tone, but you can sense it is tone. I hope you could make out the difference. The first one was broadband, whereas this one is a tone. And between chaos and order, we actually have intermittency. You will, if you pay attention, you can see that the system is trying to burst into periodic oscillations, but it's being pulled back to a periodic low amplitude, a periodic oscillation. So between chaos and order, we have intermittency. So we can replace the stable to unstable paradigm with a combustion noise via intermittency to periodic oscillations, which are full-blown instability. Okay. So we can analyze such things. Complex system theory comes with a lot of tools. So one such tool is recurrence analysis. A recurrence plot is a graphical representation of visualizing the complicated system dynamics, which is in an n-dimensional phase space in 2 dimensions. So what we do is to start some point time. So we start at this point. So this x-axis is time, y-axis is also time, and we draw a epsilon ball around this point. And if the next point is within this ball, we put a black dot. If the point is outside the ball, we put a white dot, and we go through the entire trajectory, and we start with different times and fill up this picture. So you can think of it either as a matrix or as a plot. So when you have limit cycle oscillations, you start from some point here, and then after some time it will come back. After time period of t, it will come back within the circle, and again after time period of t, it will again come back. So you will see diagonal lines which are evenly spaced. Now quasi-periodic, you will see diagonal lines which are non-evenly spaced, and they will be broken. And for intermittency, you'll see black patches amidst this black patches of squares and rectangles among this white patches. So black patch means that the trajectory is stuck inside this epsilon ball. So human beings can detect patterns from our earlier life in the forest. We are very good at pattern detection. That is how we survived. So recurrence analysis makes use of this ability that humans have. So if you go from stable operation, so you get a grainy plot, that is a recurrence plot. And unstable here is like a plot full of diagonal lines, very ordered. And in between your intermittency, you have patches, black patches, but there's also short length diagonals. And we can also look at the properties. So the picture here is pressure amplitude. The diamond-shaped blue things, they are the RMS value, and the star is the FFT peak. So they are going slowly and then going up at some point. Whereas well before this move, the recurrence rate, which is the density of the black points in this plot, or trapping time, which is the amount of time the trajectory stuck inside this epsilon ball, they come down. There are many such measures, for example, Shannon entropy and so on. So these work as very nice precursors to the onset of thermoacoustic instability. You can know well in advance whether instability is going to come or not. So next we look at fractals and multifractals. That is another way with which you study complex systems. So a chaotic time series has a self-similar behavior often, with patterns that fill non-integer dimensions. So combustion noise signal appears to be self-similar. That is, the signal has fractal characteristics. So the top picture, you take a look, and the middle picture is a zoomed in version of the top picture, where you zoom into the first 1 second. And in the next picture, we zoom into the first half of the second plot, or the first half a second of the second plot. And you can see that the structure keeps repeating. So the signal has fractal characteristic, but we can quantify this. Well, what we do is to split the time series into small different segments. And what we do is to plot, you find the in a plot in a log-log plot, the RMS of standard deviation fluctuations as a function of the time scale. And we do this in a log-log plot. And you could take scaling over some range. So for a periodic signal, you will not get any scaling. So the scaling exponent will be close to 0. For white noise, you'll get a scaling of half. But for things like thermoacoustic instability, you will get a scaling which is in between both these two. So this is the characteristic of stable operation. And so we can look at the transition to thermoacoustic instability. On the left side is the data from a soil burner. On the right side is data from a bluff body combustor. And you can see that we are plotting the yellow is the RMS value of pressure, and the dark blue squares, they are the FFT peaks. You see that the first 4 points, the amplitude hardly changes here, but you can see that the Hurst exponent is plummeted in the first 4 values. And here you can see on the right side, it's maybe even more dramatic. For the first 10 or 12 points, there is hardly any change in the pressure amplitude. You see this line stays flat, but you look at the Hurst exponent, it is actually falling very rapidly. So the Hurst exponent approaches smoothly to 0, unlike the pressure amplitude rise, which is rather dramatic. So Hurst exponent is a very good precursor to the onset of thermoacoustic instability. So as we approach any bending instability, we see Hurst exponent approaching 0, and we also see a loss of multifractality. So the amplitude actually has an inverse Koala scaling with Hurst exponent. So this is true for any combustor. You can take soil combustor, bluff body combustor, you can change the length of the combustor. You can take, we have actually looked at data from so many different combustors, but we only put whatever we did in our lab here. You get the scaling. Amplitude goes like 1 over Hurst exponent squared, so the inverse square law. But what is interesting is this is true for emergence of periodic oscillation, any turbulent flow. So it is true for an aeroacoustic system or an aeroelastic system, also turbulent system. So this is a very fundamental aspect of order emerging from turbulence. Now, the amplitude also has other scaling laws. So if you take the FFT and find a spectral measure based on the moments, so this mu naught is the first zeroth moment, and mu2 is like the second moment, and we can plot them. So this spectral measures, there are many spectral measures, and you can see that they actually you have a scaling with a very definite slope, and you can see so many things are falling into scaling. So the combustors, bluff body combustor, swirl combustor, aeroelastic system, aeroacoustic system, this electronic circuit is a Chua circuit, random laser, and many different models. So this is something really fundamental. So next I want to look at complex networks. So in a complex network, we have nodes that are connected by edges. And this is a fundamental tool to study complex system, because complex system has interacting components. And so this is a very natural way to find the interaction between nodes. Okay. So there are many different ways to construct complex network. The simplest one is to use what is called a visibility graph. So we pick the peaks in the time series and we connect one peak to another peak. And if this first peak can see this peak, then I connect the line. This can see the second peak, I can connect the line. But the first peak cannot see the third peak because the second peak is blocking it, so I don't connect the line. So it's as simple as that. And basically, we are capturing the slow flow evolution of the system. So we try to characterize the time series of the thermoacoustic system using complex networks. And we see that if P of K versus K, what is it P of K? P of K is the fraction of nodes having K number of connections, and K is the number of connections for each node. So this follows a power law, or log of P of K versus log of K follows a straight line in this log-log plot. So such network with the exponent between 2 and 3, here its exponent is gamma equal to 2.7. We take several different combustors, we get same kind of thing. And such graphs are called, such networks are called scale-free networks. In fact, this was discovered in 1999 by Alberto Barabasi, and there are so many different systems in the world, including internet, the World Wide Web, and airline network. They all follow such a scaling, such scale-free network behavior. And we can see that our thermoacoustic system is also doing it. Okay. So now what is interesting is when we change from stable operation to instability, this scale-free network actually transitions to a ordered network or a regular network. So that is, the transition can be seen as a change in the topology of the network. So, and therefore you can use the measures that quantify the network. Various measures are there, the statistical mechanics of complex network. They can be used to characterize, to find out how close you are to the onset of instability, proximity to the onset of instability. And we can also use other things like recurrence network, where we actually construct the phase space, and if 2 points are close, you connect. If 2 points are far, you don't connect. And this first one is a what is called combustion noise. This is intermittency or the stable operation. The second one is intermittency prior to thermoacoustic instability. You can see the nice band corresponding to the periodic burst, and then the other stuff is corresponding to the aperiodic part, and this is the nice limit cycle. And there's intermittency after limit cycle, and you see it's a very fascinating structure. And then this is the structure of the oscillations prior to blowout, and then you have I drew a picture of a random network, and that's completely different from these things. And you can have measures which quantify this, and we can also get precursors, and you can do a lot of analysis. But I'll just introduce recurrence network here and leave it there. Now, thermoacoustic instability is really the result of coupling between hydrodynamics, flame, and acoustic field. This is a picture I got from Isaac Box and Ianco Cetre from DLR Stuttgart. And you can see that there is an interaction between flame dynamics, hydrodynamics, and duct acoustics. And so we can see how these things synchronize with each other using tools from synchronized theory, and see how there is synchronization between the subsystems leading to self-organization. So if you look at the time series of acoustic pressure, which is the black color curve, and red is heat release rate, you can see that during the stable operation, these acoustic pressure and heat release rate are desynchronized chaos, whereas during the intermittent phase, they are synchronized during the periodic epoch and desynchronized during the aperiodic epoch. And then you get to a low amplitude periodic solution, or low amplitude weakly correlated limit cycle, where you have a state called phase synchronization, where the phases are dot, but not the amplitudes. And then we go to a state called generalized synchronization, where one curve can be written as a function of the other curve, and there the amplitudes are also staying nicely. So we go from desynchronized chaos to intermittent phase synchronization to phase synchronization to generalized synchronization. Now, so far I've been speaking about time series analysis. So let's look at spatiotemporal dynamics. So thermoacoustic instability we know is caused by positive feedback between sound and heat release rate. So we look at the phase angle between them, and that's the best way to quantify the interaction. And the top left is during stable operation or combustion noise. You can see that the phase field is incoherent. Bottom right is thermoacoustic instability, very coherent phase field. And during intermittency, top part is the periodic part of the intermittency. Intermittency has both aperiodic and periodic part. So here is the periodic part, and you see here a coherent part, and here is the incoherent part. And if you plot these phasors as arrows, you can get a picture very similar to phase transition in statistical mechanics. And you see that during combustion noise, we have disordered phasors. During thermoacoustic instability, you have lined up phases in order. And during intermittency, we have a state where order coexists with disorder. This is called a chimera state. And this name was given by Abrams and Strogatz in 2004. Chimera was discovered by 2002, but the name came in 2004. So chimera is like a Greek mythological monster with had two heads, lion and goat, and serpent as a tail. And that means there are many states coexisting simultaneously. So physicists found it surprising in the beginning. They first found it theoretically, and then they rigged up a lot of experiments, coupling 3 lasers and 4 lasers and so on. But thermoacoustics, we don't have to rig anything. In turbulence flow, order emerges from chaos through a chimera kind of state. And the regions of disordered and ordered phases, they change with time. So such a state is called, by physicists called it breathing chimera. So the coupling is spatiotemporal, since the flame is spatially extended. It's not a compact, it's not heat source at just one point, it's spread out, the flame. So intermittency is the gradual emergence of temporal pattern. If you look at the time series, we saw that. And a pattern is any repeated, regularly repeated arrangement. So patterns are ubiquitous in nature. So we see patterns in fish and zebra and so on. Lots of everything in the world is a pattern, right? On a lab, you can see Belousov-Zapotensky reaction, very famous reaction, Nobel Prize to Prigogine for explaining this. So other patterns in turbulent thermoacoustic systems. And if you look at the P prime, Q prime, which is the acoustic power and how they are distributed, you see it's a grainy structure. It's not very coherent, and coherence is only in short term. If you zoom in, you see short length coherence, but not over large length. And if you look at the periodic epoch of intermittency, again, it's grainy, you don't see a lot of coherence. But if you look at periodic epoch of intermittency, you can see the emergence of coherence. And if you look at thermoacoustic instability, you see large regions of spatial coherence emerge during thermoacoustic instability. So if you look at this movie, this is during the stable operation, and you can see that there is disordered emergence of small scale vortices, and they keep going. And now if I look at thermoacoustic instability, you see that there's some kind of collective interaction that leads to order at large flow scales during the onset of thermoacoustic instability. The large vortex is composed of a lot of small vortices actually. So the interaction at small scale causes self-organization. At the large scales, in the flow field. And we can see that in the chemiluminescence field, actually, this is during stable operation. We see disorganized motion, or only organization over a very short length scale. And this is the velocity vector field. And now we look at thermoacoustic instability, and we can see that there's some kind of pumping, very large coherent motion. You can see the thing is pumping. It's very neat, this very large scale organization. And also we observe a very large coherent structure in the PAV field, velocity field and the vorticity field. You can see this large coherent structure emerging. So the onset of thermoacoustic instability is indeed the onset of a pattern formation. So there is the acoustic field, which is one pattern with a coherent acoustic field. The other pattern is the large coherent structure, and you can see it in the flame and the acoustic power generated and so on. So I would say that the small scale interaction within the flow field takes place, resulting in the formation of large scale structures. And the process by which the small scale interaction takes place within a subsystem results in the emergence of order at macro scales. This is the pattern formation process. And we should distinguish this from the interaction across subsystems, which we can think of as coupling. So in the absence of patterns, the coupling itself is disordered. And once patterns form through the small scale interaction leading to large scales, then the coupling becomes more ordered. So in reality, possibly it's a two-way process through which the coupling across the subsystems reinforce the patterns, and the patterns in terms reinforce the coupling between the systems. So this is what we have tried to represent here. Thus, at the onset of thermoacoustic instability, we see mutually sustaining patterns. There is one pattern is a large standing wave pattern in the acoustic field. The other pattern is large coherent structures in the flow field. So this is viewing the subject through the lens of complex system theory. So I'm running out of time. I'll skip some of the stuff and get to mitigation measures. So we'll talk about smart passive control. So we compute the network, and there's several different ways to do it, but I will look at a spatially weighted correlation network. Correlation network means you look at 2 points and take some data, vorticity or velocity or heat release rate, and find the correlation of one point with another point. Okay, so here we use velocity, and we divide the turbulent flow field into grids because it's coming from PAV, and each of these cells is a node in the network, and look at the correlation between them. And the correlation is below 0.5, we don't connect them. The correlation is above 0.5, we connect them, and we use the strength of the correlation as the node as the weight of the connection. Okay, so we can see that we can plot various parameters such as node strength, which is the sum of the weights in a node, or we can have look at clustering coefficient, which is the ratio of the number of connected pairs of neighbors in a node, the total number of connections in the neighborhood of a node. Or we can look at a measure called closeness centrality. There are a lot of centrality measures which tells how central a node is to something. The closeness centrality measure quantifies the average shortest distance of a node with all other nodes in the network. And you can see whichever way you look at, there is a region here which has high value of this measure. So the region on top of the bluff body shaft is emerging as a critical region during the onset of thermoacoustic instability. So usually we do passive control by trial and error, but there is a possibility to do, this is very expensive and many times it will fail. But can we do a smart passive control by disturbing this critical region? So what we did is we inject microjets at the different locations and try to see where we suppress. Of course, we know from this picture that this is the critical region. So if we inject a jet into it, it actually suppressed the sound pressure level to the levels of stable operation actually. Whereas if we injected other place, the sound didn't come down. So this region is optimal location for implementing control strategies. And actually we took images and calculated the network without injection and with injection. And we see that when you inject, this critical region actually is disappearing. So that we are successful in reducing the amplitude of the oscillations because of that. And we have recently published a paper which actually shows that these regions are indeed the hubs based on vorticity networks and so on. So they are really like the hubs are considered Achilles heel of the network, the weak point. And this paper gives a lot of detailed calculations and detailed way it's proven that these are critical points. So I think I'm at the end of the time. So in summary, nonlinear dynamics and complex system theory provides frameworks to analyze data and predict and control thermoacoustic instability. And recent efforts to apply bifurcation theory, synchronization theory, fractals, recurrence theory, and complex network to problems in unsteady combustion have yielded rich dividends in obtaining insights to the problem. And this has been implemented in the industry. This is our patented technology and copyrighted software with which this has been worked in several different cases across different establishments. And complex systems are known to display pockets of order amid disorder. During intermittency, we find bursts of high amplitude periodic oscillations, which corresponds to pockets of order, and this is scattered amidst epochs of low amplitude periodic fluctuations, which corresponds to pockets of disorder. And synchronization theory reveals that during the occurrence of intermittency, we see chimera states. It's very exciting. This is something physicists predict will happen, and it has happened naturally in our system, where pockets of order coexist with disorder. And during the emergence of order, large coherent vortices emerge from because it's an emergent quantity. It's not a shed quantity, it's an emergent quantity. It's coming because of the collective interaction between the small vortices. And a beginning has been made to study the spatiotemporal dynamics of thermoacoustic systems using the frameworks of synchronization theory, complex network, fractal and multi-fractal analysis, and pattern formation. The study of the spatiotemporal dynamics is indeed the next frontier. This is a cartoon from a very nice paper on complex network by Yakubela et al. And it talks about various things you can do: coherent structure identification, low order modeling, extreme event characterization, regime transitions, early warning indicators, flow control strategies. So improving our understanding and control of complex, improving our understanding and control of thermoacoustic instability will require the application of the latest advances in complex system theory. And for this, what is important is that researchers doing laser diagnostics and large eddy simulation need to work together with researchers in complex system theory. And we need to transcend the boundaries between engineering, physics, and mathematics. And then we'll have success. Because one person cannot do laser diagnostics and complex system theory in LES. So we need to have this kind of network of people doing this. And that would be what will be, the next decade would be characterized by that, I think. So also machine learning is making rapid progress. So deep learning in conjunction with network analysis will be a powerful tool in analyzing, prognosing, and controlling thermoacoustic instability. And in a thing like power grid or internet, the connections are physical, whereas in a turbulent flow, the connections are abstract. And complex network theory, this framework provides a framework to represent these abstract connections. And machine learning methodologies can identify patterns in these networks and learn to predict the evolution of these patterns. And I think this will make a big deal towards recognizing and finding these instabilities, understanding them, and eventually controlling them. So the real test of complex system theories, you can do all the maths that you want, but the real test is that its ability to provide something useful to the designer to mitigate thermoacoustic instability and to the engineer on the field to evade it. And already we have had very good success on this. And I really invite you all to come and work on this very exciting topic, which is yielding really incredible returns, actually. So some references, this is a paper in Proceedings of the Combustion Institute, which I have written together with Vishnu. And this is another one on a perspective article on this complex system perspective written by me and Vishnu. And this is an annual review article written by together with Matthew Juniper from Cambridge. So we turned in a book to the publisher. This should come in 2 months or so, which will have all the details of all these things and a very detailed description of the tools and how you can do this. And so let's come back to Strogat's picture. So he has, we have high degree of freedom, high number of variables, and high level of nonlinearity. And this is spatiotemporal complexity. And here, this is the cutting edge in physics, actually, nonlinear physics. So, and turbulent reacting flows falls right in here, maybe even much more complex than any of the systems described here. And this is the frontiers. So physicists have been using Rayleigh-Bénard convection as their benchmark problem for studying this complex system theory, but I think it's time we bring thermoacoustic instability to their attention. This problem is really challenging, and the tools from physics have to be really stretched to be able to study this. This is the height of complexity. So turbulent reacting flow is the height of spatiotemporal complexity, and the complex system theory itself needs to be advanced to accommodate the complexities of turbulent reacting flow. This is indeed an exciting prospect. Thank you.
Thank you very much, Professor Sujith. It's very wonderful talk with a lot of content. We do have, I would say, many questions. So let's see if we can go through all of them, or at least some of them.
Okay.
So the first one, let me see. Maybe I cannot pronounce the name clearly. It's one from Koshbara. I hope
Yeah, okay. Is it possible to obtain an effective theory that describes emergent behavior by integrating averaging out short? Yeah, I really think this is the key to solving the problem, to average out the short distance degrees of freedom. So this needs skill in renormalization group theory. I think this is definitely the thing that needs to be done, but it's not that easy. It's easier said than done. So if I teach myself renormalization group theory for the dynamical such complex systems, I think it's definitely possible.
The one from Jackie is Professor Sujith, you just mentioned that the intermittency occurs between the chaos and order state. I just wonder if the intermittency could occur between the two states of order. For example, one limit cycle oscillation with lower amplitude and another limit cycle oscillation with much higher amplitude.
Absolutely, it does. We have seen this in the lab, and we are in the process of writing up something on this. But this is definitely possible. This does happen.
Okay.
Very good question.
So the next one is from Professor So Yang. He asked it, when we do spectral analysis of turbulent thermoacoustics by FFT, how to tell whether a signal feature comes from turbulence cascades or from thermoacoustic instability?
Yeah, so if you look at the pressure signal, we can't quite separate out as one thing is turbulence and one is acoustic, because although the system has acoustic and turbulence, we can't simply separate them out because it's a nonlinear system. So, but the key thing is that when you if you think about it as a mode, it's a monolithic mode. So if you transition from stable operation to unstable operation, this all we can say is that the FFT steepens, and then there is a very definite law, very definite scaling behavior with which this energy is pumped into the acoustic mode. So in the end, I think if you look at the pressure spectrum, you would see everything you see is probably thermoacoustic, but in velocity spectrum, you would have both the cascades, but I think more work needs to be done to be able to clearly say this. Okay, a very nice question, and a lot of work to do to show this.
Yeah, I think the point is if it's pressure, then as long as you are not kind of in the vertical structures region, then the pressure will be the acoustic pressure.
Right.
For the velocity,
if it is velocity, you will have both the cascades in it. And
yeah,
a lot of work needs to be done. Okay.
Okay, so the next one is from Aruri. So irrespective of the Bernard type, the plot for heuristic plot has very similar, almost identical slope. Is there any physical explanation for this pattern?
Yeah, so that's the key thing of the way the universe works. So if you look at equilibrium phase transitions, whether you look at ferromagnetic to paramagnetic transition or some crystal changing structure, any different type of phase transition, you get certain scaling, the Vidom scaling, and which has been worked by Wilson. Wilson got Nobel Prize and Kadanoff on that. And what they showed is that irrespective of the different physics, you get the same kind of behavior, because you average out the first question, which was about averaging out the short distance correlation, and the way the large scales come from this is based on the interaction between the scales. So irrespective of the physics, so what I'm trying to say is that irrespective of the physics, you will get the same behavior. That's the way the things are, and because it's underlying, there is a common bifurcation. So you don't need independent system with independent different physics have the same behavior.
I also feel that's a very amazing part.
Yeah, we did lots of experiments on lots of systems, and we found identical scaling laws.
Yeah, so that is the reason why you can use that as a precursor for either the instability or the amplitude. So the next one is from Raman. Out of curiosity, does the inverse power law of scaling has any dependence on equation of state at which combustor is operating? For example, in liquid rocket engine combustor, where we have in general supercritical fluid state, transport properties are very highly nonlinear near the critical point.
Okay, so I have not done anything with supercritical fluid state, but I think as long as you have large amplitude bursts interspersed between small amplitude bursts, we are getting the scaling, and we are getting the same scaling in systems without combustion or with combustion. Like aeroacoustics have no combustion, aeroelastic has no combustion. But of course, it would be interesting to look at such data, and you can contact me over email, and I'll be very happy to discuss this and maybe calculate for this. I don't have such time series data.
Okay. So the next one is from a Voghesh. It is very interesting to see how complex systems theory can characterize different states of the system, such as stable intermittency and thermoacoustic instability. Does the theory provide a framework for how, when, and why the transitions happen or occur?
Right. So one such framework would be using cellular automata, the complex system theory, which actually says that you should focus on the interaction, not on the detail of the system. So we can, we have done actually blowout using this theory actually with cellular automata by just focusing on the interaction. So it's possible, and similar theory can be made for thermoacoustic instability also. I think it's a matter of time before somebody does this, and people have made such theories for several different complex systems.
Okay, the next one is from Ankur.
Okay.
A very extensive talk. Can you please throw some light on thermoacoustic instabilities in scramjet engines? What is the role of high-speed mean flow? What could be possible suppression mechanisms?
Okay, I don't have any idea about scramjet engines, but I have heard a talk once where they say that through the boundary layer, the waves can go back and lead to feedback, but I really don't know anything about this. So I'm really sorry. But there's a question by Jay Gore about this, about the video showed blue premix flame stabilized by a disk. However, the flame in the wake was yellow and orange. Okay, so the actual proper videos that I showed were grayscale images with no color. This blue and yellow and orange, that was just more like we played with the camera to get an artistic looking picture to capture the fancy. So this is really not to get this yellow color, we are running it rich and so on. So it's just to get an artistic thing, but all the real serious pictures were grayscale. So I think this was just to play.
So
And
false color image, is it? False color.
Yeah, not false color, real color only. We did a lot of. I had a student who is a Manikandan, who is a professional photographer. So it was according to his sense of aesthetic. So yes, there was swoop and so on.
But
now,
you're basing
random
all of the theory on quantitative calculation, quantitative images.
Right, that's based on chemiluminescence and OH and CH, and that is those grayscale images, and they are with these filters, 428 nanometer or whatever. We put it's all quantity, and velocity is measured quantity. This particular picture is just a photographic artistry or something.
Very quickly, could you comment on, I kind of was listening very carefully. You did not use the word randomness. You kind of replaced it with disorder. So is it order and disorder? Is there no randomness in the universe?
So a very brilliant question. I cannot speak about the universe. I'll speak about the thermoacoustic system, which is my universe. So in that, we have done very extensive analysis, and we have shown that what we have during the stable operation, it looks random, but it's actually deterministic chaos. It's high dimensional chaos with the dimension, embedding dimension of like 7, 8, 9, 10, something like that. So physicists would call n equal to 5 or 6 is hyper chaos. So this is more than that. So this is high dimensional chaos, which is, of course, it's an experiment. So there will be some corruption by colored noise. So I had a student.
Is 7, 8, 9, 10 a randomly varying number, or is 7, 8, 9,
degrees
10
of freedom? That's the
number.
It's a deterministic number. So we have to put adequate number of dimensions to be able to get the phase portrait, to get the phase space embedding. So you need, I think, typically, depending on the system. So the system we had, we needed 8 dimensions to describe them. And within that, it's deterministic chaos. That means you have short-term predictability. We can clearly show. We have done very elaborate calculations, and we have published a paper in Physical Review E in 2015, where we have shown clearly that this is actually deterministic chaos. Now, we can model it as random fluctuation if you want to use a stochastic theory and so on. But here we wanted to get the precursors. So for that, we were trying to use the features of determinism. And we could, now the chaos theory is well advanced that we don't have to throw away this. So typically as engineer, we have a signal and we say, this is our signal, this is noise. But here it is a turbulent system, and turbulence is also fluctuation. So what is turbulence? Can you separate turbulent fluctuations from stochastic fluctuations? So we didn't want to do all that. We wanted to hold the bull by, catch the bull by its horns and address the system. And the complex system theory in the last 20 years is advanced enough that you can deal with it as deterministic fluctuations.
Okay, can we? You can continue the discuss maybe later. Let's try to finish as much as we can. So Professor Yannis Hadloupas asked one question. Is it possible for LES, the safety, to predict the transition to oscillations and the intermittency of the process? The complex theory characterizes the behavior of the system at different states, but does not provide information on the physical process responsible for the transitions. So are the appropriate physics present in LES or CFDs? This
is absolutely brilliant. So although the complex system theory doesn't, it talks about the interactions, and we don't need to get a detailed physics to make a model, but from the way to characterize the solution. For example, you capture a time series from pressure from LES simulation, and we say the RMS value of the pressure and so on and so on. But is it right? Will you always get the second? If this is correct, will you get the next prediction right? So the pressure fluctuation, there is a lot of money in the nature of the fluctuation. There's a microstructure to the pressure fluctuation. So can the LES simulation predict the multifractal spectrum? Can it predict the complex network structure? Can it predict the right recurrence structure? So if that is done, then your simulation is right. So I think complex system theory provides a very good way to benchmark CFD simulations. I personally feel that the CFD simulations are not currently tightly benchmarked because there are a lot of features which we are just benchmarking based on gross measures. So we are throwing away all the money, but instead we could use complex system theory to get very good benchmarking using all these measures that I mentioned. You can use all of them in CFD data, and there's a very good comparison if you can do that.
Okay, there is one from Andrew. Is there any estimation of the entropy balance available at the onset of intermittency?
I can only give a general answer. Andrea, you are the last word on this. The only work I've seen on such complex systems is by you. So I think it's an open system, and so that's why we are getting order, although the entropy of the universe is increasing, but in the system, the entropy is decreasing. But I have no calculations, and the only work I know is your work, Andrea.
Okay, there is one from another question, basically from 111. I don't know who this is.
Yeah, okay.
But anyway, in the experiment, if one uses a single flame but not multiple flames, how about the thermoacoustic instability? Are there so many non-linearities phenomena yet?
Oh yes, it's a very nice question. So the intermittent time series that I showed in the beginning, and the flame rising and falling, that was for a single flame, single Bunsen burner, most simplest flame, and it showed all this complex nonlinear behavior. That was a laminar system, and the turbulent systems that I showed has a single flame, and it had all this complex behavior. So I think it's there. It doesn't matter whether it does no requirement like you have to have multiple flames and so on. But of course, multiple flame systems also have all these things, and it's very interesting.
Okay, so I think there is one, I guess it's a comment from Cora. It's not a question. So basically, I think Sujith, Professor, you can just read through it. So yeah. I do see two more questions.
I just want to remark on Dr. Kolar's observation that I think there's a lot of commonality between thermoacoustic system and climate dynamics, for example. Of course, thermoacoustic system, the good thing is while it has all the complexities, you can do this experiment in the lab, get detailed data, whereas monsoon comes only once a year and then it's gone, and then you wait for the next year. So I think it's a very good test bed for making non-equilibrium, studying non-equilibrium physics, and make theories and test all these theories, which it's a very good test bed. And then once you figure it out, then you can apply it to other systems like monsoon network and all that. And I'm actually now working on this thing. Thank you, Ramesh. It's a very interesting point. Yeah, how to address rare events. And so, for example, before blowout, you see these rare events, and actually they're like Dragon King. We have a paper coming up next week on Europhysics letters. So we can do a Dragon King analysis where you have a distribution and the thing doesn't fall on that distribution. And we are actually capturing it as a Dragon King event. And I think I'll send you the paper when it comes out probably next week. Okay, how effective is
to send the paper? I'd love to continue the interaction about rare events.
Right, that's a very interesting topic. I've just recently got something worked out on that, and I'm wanting to work more on it. So we did something with Dragon Kings. Thank you. Very interesting point.
Yeah, thank you.
How does anti-sound as an active control, active instability control? I think I'm certainly not expert in it, but people have demonstrated the effectiveness of anti-sound or active control in the 90s or late 80s and so on. Dowling's pioneering work and a lot of work at Georgia Tech. But somehow it is not being implemented in the system. So when I speak to the engineers from these companies, they say that it's because they don't trust the actuators. But is that the truth, or they actually don't trust the theory behind it? I don't know. So maybe there's some things which nobody uses it and suddenly it becomes very active. For example, machine learning was an exotic subject, but now all of it, nobody used it, and everybody thought it was something which geeks did, but not anything practical. Now everybody using machine learning. So like that, it may be possible that some 10 or 15 years later, active instability control would come back with this modern flow control theory and so on. So in the immediate future, I don't see any movement as I hear, but I think long-term prospect must be very good. In aeroplanes, they do it, right? They fly unstable planes. So why not unstable combustors? So I guess things are not there yet.
Okay, I think I have one last question.
Yes,
so how feasible is it to use the precursors like the Hurst exponent in real-life systems, for example, in gas turbines, running in power plants? If I understand correctly, precursors are easily obtainable in quasi-static experience,
right.
but not in a real-life continuously running system.
See, we have to look at the time scale of the system. On one hand is this power plants where instability, the change of parameter is the order of minutes actually. And we need like half a second or 1 second to get enough convergence, you have to acquire enough data to be able to make a prediction. So if it's a low frequency problem, we need 1 or 2 seconds. If it's high frequency, then maybe 0.2 seconds, 0.3 seconds, which is much smaller than the time scale over which the instability comes. Now, if you on the other extreme, where you look at the fighter aircraft and you have 0 to full throttle in 5 seconds or something, go from 0 thrust to full thrust, and typically if the instability has come, we need like 0.2 seconds, 0.3 seconds. So I think it's really feasible.
Okay.
I think, yeah.
So basically, it needs to be fast.
Yeah, I mean, this precursor calculation is not a showstopper. It is what you can do with it, whether you have the deployment. So it's the engineering thing, whether you have money, whether you're engineered to do this, all these things. But precursor technology works, that's not a problem.
Okay. Okay.
It works very well. Like, even for rocket situation, it works very well. Liquid rockets. But there, you may not want to do any such things. But in test stands, we have tested.
Okay. So I think we finished the big majority of the questions. So I think we are almost done here. Thank you very much, Professor Sujith. It's a very wonderful talk, and we have a lot of questions and a big number of audience. So thank you very much. I don't know if Professor Yuguangju want to give any comments?
No, it was a great talk. I don't have any additional comments. That's the only thing. Great talk. Thank you, Raman.
So I want to remind Professor Ju of a picture that he likes to take, of a picture of attendees or panelists or something like this.
Okay, thank you very
Just
much.
for memory's sake, of the great program that you organized.
Thank you very much, Jay. And right, thank you everybody. And if you want to turn on the camera and say hi to Raman, you're welcome.